going to do to start with is finish off the set of notes that will be covered on exam 3. All right, so what you can think about again is for exam 3, you've got 2 sets of notes to cover. The one where we talk about the definitions of acids and bases and we define pH, and then this second set where we talk about determining pHs and identifying different types of solutions. What I'm going to, that'll take me about 5 or 10 minutes to finish off. And then we'll get into a new set of notes where we're actually going to look at buffers in much more depth in terms of what can happen to buffers when we stress them and the calculations associated with that. And that will carry into titration curves. But that material will be on exam 4. All right, so let's go to where we left off a week ago. And what we were doing is the last hurrah for this particular chapter was we were exploring diprotic acids. And I categorized them differently, but the reality is, as we shall see with this particular problem, that in most cases, it's only one Ka value that's going to have a significant contribution to the pH. And that's definitely true with acids like sulfurous acid, because if you look at the 2 Ka values, and again, they vary from one book to another, you find a huge difference. There's about 6 orders of magnitude difference between the two, all right? I'd say about 500,000 times different. Okay, so the Ka2 is 500,000 times smaller than Ka1. And that tells you something about its contribution. And so what we did at the end of class a week ago was we went through this calculation where we set up using Ka1 how much hydrogen ion will be present in this solution. And we found that from Ka1 alone, the hydrogen ion concentration is going to be about 0.03 molar. And then what we started to do before we ran out of time was we set up the same thing for the second equilibrium, okay? And again, we're looking at this stepwise, which is perhaps a little bit of a stretch, but it does work, and it works for our intents and purposes. So the way we looked at this is we said, okay, we allow this first Ka equilibrium to come completely to equilibrium. And if so, what happens is we see the concentration of the conjugate acid in the second equilibrium and the concentration of hydrogen ion are both the same to start with. And the concentration of the hydrogen ion is going to increase by some amount, and the concentration of the conjugate acid is going to decrease by some amount. All right, now, and again, this Ka2 is very small. So let's continue with that. I actually asked you to do this on your own, and hopefully some of you did. The value of Ka2 is 6.3 times 10 to the negative 8th. Now, according to our ICE table, the concentration of hydrogen ion is going to be 0.030 plus Z molar. Concentration of the conjugate, the second conjugate base is going to be Z molar, and the concentration of the first, or the conjugate acid, the second conjugate acid, or the first conjugate base is going to be 0.03 minus Z molar. And so, again, we could ask ourselves, is it valid to make an approximation here? Of course, we could solve for a quadratic if we want to, but again, we can use the idea of the approximation to say this, that if we add Z to 0.030, or we subtract Z from 0.030, that's not going to make much difference. And again, our basis for doing that very simply is we take 0.03 and we divide it by 6.0, or 6.3 times 10 to the negative 8. That's going to give us a quotient that's much larger than 150. All right. Now again, we can prove that. If we go back to this equation and we substitute that in, we say, okay, now 6.3 times 10 to the negative 8th is equal to 0.03 times z divided by 0.03. Makes solving this a whole lot easier because we're dividing the same number by itself, and so what we end up with is this. The z value that we get is the same as the Ka2 value in terms of magnitude. All right, so it is really small. All right, so if we go back and we say, okay, given what we figured out from the first part, the concentration of hydrogen ion we got was 0.030 molar. And then we're going to add this tiny value to it. Essentially what we end up with is this. In this solution, the concentration of hydrogen ion comes primarily from the first dissociation. All right, so this is what you can think about with regard to polyprotic acids such as this one. In most cases, the Ka1 and Ka2 values are more than 10,000 times different. And as a result, if you're dealing with a solution of the pure acid to start with, then to get the pH of the solution, all you have to do is use Ka1, because Ka2 is not going to have a significant contribution to that pH. All right. If I add 6.3 times 10 to the negative 8th to this 0.030, it's not going to change the value of that number at all, at least in terms of the precision. So all we have to do then is, again, we could skip the second part unless there's more information that we need from this solution. But at least if we're just determining the pH, just use the Ka1 and treat it like a weak monoprotic acid. And so all we're going to do is we're going to take the log of 0.030, and that's our pH. So this solution would have a pH of 1.52 by our calculations. All right, now there's one other thing I want to do with this. We calculated the concentration at equilibrium of the first conjugate base. All right, it's the same as the concentration of the hydrogen ion, effectively, even though it's slightly smaller because of the ice table. But what about this? We want to figure out what is the concentration of the sulfite ion in this solution, the second conjugate base. All right, and what we can do is we can go back and look at our work. And essentially, by this, the only place that the sulfide ion appears is in the Ka2 equilibrium, right here. And so, in this particular case, what we can say is the concentration of the sulfide ion is going to be equal to the value of Z that we got, which is the same as the Ka2. And now I'm forgetting what it is. It is 6.3 times 10 to the negative 8th. So we would figure that this solution would have a very small concentration of the second conjugate base, 6.3 times 10 to the negative 8th molar. Another facet of this, though, and this is something you can think about, is if you make a solution of sulfite ion, as in sodium sulfite, then that solution would be basic. And indeed it is. Okay, there's a certain bitterness associated with sodium sulfate. Okay, so again, up until here is what you need to know to prepare for the exam a week from Wednesday. What I'm going to cover next really does build on this. but it's kind of different because it's going to add some more ideas to things. All right, so let's see. Let's get in here. So what we're going to do is we're going to continue in chapter 17. And we're going to do two things first. We're going to start by looking at buffer solutions and what happens to buffer solutions when we stress them. And then the second thing we're going to do is we're going to do titration calculations associated with pH. One of the things that you want to come into this with is, first of all, this is building on things you've already learned, okay? If you can identify solutions well, that's something you think you should think about, right? And there was a Canvas quiz about that you should have looked at, all right? I actually haven't looked at the results for that one. I looked at the results for another one where you had to decide whether salts were acidic, basic, or neutral. And what I can see from that is a number of you need practice, although Canvas was pretty harsh in the way it graded things, and so I fixed that up a little bit as well. Because a number of you got almost perfect and didn't get any credit for it, which I found to be not good. Anyway, the other thing that you want to think about, and this is also useful for the exam a week from Wednesday, is identifying solutions. You have a solution, you have to determine the pH of the solution. What kind of solution is it? All right, and there was a very quick Canvas quiz that went through that, and you might want to take a look at it. And I'm going to see if I can open it again for practice as well. One other thing you need to be aware of with this section of the course is that Alex, in my mind, is missing a lot of material here. All right, so if you look at the Alex assignment for this section, it's very short. All right, now I'm going to have to supplement that. I'm going to put together some Canvas questions that delve into these things that we're talking about here in much more detail. So you definitely want to keep your eyes open for those things. And the first one of those assignments should go live either tonight or tomorrow morning, depending on my timings. All right. So you want to start taking a look for that as well. And again, really what we're doing is we're building on ideas that we've already learned. There's nothing new that I'm doing here. All right. Much of what we're going to be talking about in this particular case, or this particular section, is stuff that we've just finished talking about in the previous chapter. But what we're going to do is we're also going to apply some of the ideas of limiting reactants to this in order to flesh things out. All right, so here's a question that you can do, or you should be able to do, for the exam on Wednesday next week. And that is, if you have a solution that contains hydrofluoric acid and sodium fluoride, how do I determine the pH of this solution? And the first question I want to ask myself is, what kind of solution is it? Which of the 5 types of solutions that we've talked about, strong acid, strong base, weak acid, weak base, or buffer, does this one fit into? Well, what else do you see though? There is a weak acid in here, but there's something else. Yeah, you got a buffer, right? Okay, because we not only have the weak acid, but we also have the sodium salt of its conjugate base. So this particular solution we would peg as being a buffer. All right, and of course what that means is that we can solve it with the Henderson-Hasselbalch equation. All right, and so the first thing we need to do then is we need to look up what is the Ka value for HF. We've done that several times before, so you might just have, I mean, the easiest way to find it might be just to flip back in your notes. What Ka value did we use for HF? Okay, 7.1 times 10 to the negative fourth. Yeah, that's the value that your textbook uses. And again, if you look at other tables, you might see 6.8 times 10 to the negative fourth. So what that should tell you right away is that for some of these questions, there's going to be some variability in the answers that you get because it depends on where you look up the Ka value in the first place. Okay, so if I'm going to use the Henderson-Hasselbalch equation to determine the pH of this buffer, what do I need to get from this Ka value? Yes, the pKa. So what is the negative log of 7.1 times 10 to the negative fourth? Okay, 3.15. All right, so what we're going to do then is we'll plug this into the Henderson-Hasselbalch equation. The pH of my buffer is going to be equal to the pKa, which is 3.15, plus the log of the ratio of conjugate base to conjugate acid. Now, what do we notice about this ratio? Yeah, it's 1 to 1. Okay? Does anybody remember what we said about buffers that are like this, where you have the same concentrations both of conjugate base and conjugate acid? What's true about the pH of a buffer like this? Yeah, in this particular case, this buffer is going to have the pH of a pH that's equal to the pKa of the weak acid. All right, and that's true. That's something you want to be able to identify because there are going to be times when it's very useful. We talked about this last chapter. We'll talk about it a number of times as we go through the material in this section as well. If I have a buffer like this where the concentrations of conjugate acid and conjugate base are the same, then the log of the ratio is going to be 0 because the ratio is 1. And so the pH of the buffer is going to be equal to pKa. All right, so nothing new there. And again, this is something I expect you to be able to do for the upcoming exam, the third exam, as well as the fourth exam, because it is relevant to the fourth exam. All right, so here's what we're going to do. We have this buffer solution. We know the pH of the buffer solution based on the Henderson-Hasselbalch equation. What we're going to do is we're going to stress it by adding either acid or base to the buffer. And in order for me to do that, I have to figure out one additional thing, right? If I have a liter of this buffer, I want to know how many millimoles of conjugate acid are present in this buffer solution and how many millimoles of conjugate base are present in this buffer solution. And the way I'm going to do that very simply is I'm going to multiply the molarity of the species in question times the volume in milliliters. Okay, because molarity times volume in liters will give me number of moles. Molarity times volume in milliliters will give me number of millimoles. And so if I want to get the millimoles of HF, I'm going to take the concentration of the HF, which was given to me as being 0.15 molar, and I'm going to multiply that by the volume of the solution in milliliters. Okay, so 1 liter of solution is 1,000 milliliters. And so what that does in this case is it tells me that this buffer solution contains 150 millimoles of HF if I have a liter of it. Similarly, I could say how many millimoles of F minus are there, okay? F minus being the conjugate base. It's sodium fluoride in this case, but the actual conjugate base itself is fluoride ion. And again, the concentration of fluoride ion, based on what we're told, is 0.15 molar. And again, the volume of the buffer is 1,000 milliliters. And so if I have a liter of this buffer as I have made it here, then I have a buffer solution that contains 150 millimoles each of conjugate acid and conjugate base to start with. Okay, so we're going to do two different things, and actually we're going to do another thing in the middle of it to demonstrate what a buffer can do. All right, so here's what we're going to do to start. We're going to take a liter of this buffer and we're going to dump in some strong acid. And we want to figure out, okay, how is that addition going to affect the pH of this solution? All right, now there's several options. If I add acid to a buffer, the pH of the buffer will go down. Okay, that's the first thing you want to know. But will it go down by much? And that depends on how much acid you add to the buffer. All right, so here's what I'm going to do to start with. If I add acid to a buffer, the acid is going to react with the conjugate base that's present in the buffer. So in this particular case, if I add a strong acid, HCl, that's adding H plus to the buffer. That H plus is going to combine with fluoride ion that's present in the buffer, and it's going to make more conjugate acid. Now, we are writing this net ionic equation like it goes to completion. And for our intents and purposes here, that is a reasonable thing to do. All right, so let's go back and think about this. Well, what did we say to start with? We have a buffer that's present that has 150 millimoles of conjugate acid and the same number of millimoles of conjugate base. Now we have to figure out, okay, if we're going to add a strong acid to this, and a known quantity of the strong acid, how many millimoles of hydrogen ion are added if we add 15 milliliters of a 1 molar solution? Remember, millimoles is volume in milliliters times molarity. So how many millimoles is this?
15.
Yes, exactly. 15 millimoles. All right. So my two reactants are going to combine to make more product. But the progress of that reaction is limited by one. Which of my two reactants is my limiting reactant? Yes, exactly. So what I'm going to say is, okay, all of the H plus gets consumed because it has the lower number of millimoles. It takes with it the same quantity of the conjugate base, and it produces that quantity of conjugate acid. So in a way, this is kind of like an ice table, but we're using it instead to describe limiting reactants rather than equilibrium concentrations directly. And so if this goes the way we say it does, then in the end, we're going to produce 165 millimoles of conjugate acid, and we're going to be left with a solution that contains 135 millimoles of conjugate base. Is this still going to be a buffer? Does this solution still contain appreciable quantities both of conjugate acid and conjugate base? Yeah, it does, exactly. So we would say, all right, we've changed the nature of our buffer, but we haven't broken it. Okay, it's still a buffer. We still have a large quantity of fluoride ion, a large quantity of HF. All right, and we also know so that means we can use the Henderson-Hasselbalch equation to figure this out. All right, so literally what we're going to do is this. We're going to say, okay, the pH of this buffer is equal to the pKa that we determined previously, plus the log of the ratio of the concentration of fluoride ion to the concentration of HF. All right, so let's figure out what each of those concentrations are. All right, let's start with fluoride ion. In our resulting solution, the concentration of fluoride ion is going to be 135 millimoles divided by the total volume of the buffer solution. Now, we started with 1 liter of the buffer, so that's 1,000 milliliters. But then we also added 15 milliliters of acid. So if we assume those volumes are additive, we get this. So we're going to take 135, we're going to divide it by 1,015.